So at the beginning of this chapter, or this section 17.3, I said that vector fields are like a new idea, but that's not entirely true. We have seen vector fields before, we just didn't call them vector fields. But when we computed the gradient of a scalar function, we really generated a vector field. So for example, when you look at the function f of xy equals x squared plus y squared, it's been a while that we talked about gradients, but you hopefully remember that to get the gradient of a scalar valued function like that, you take the derivative with respect to x. That gives you 2x. You take the derivative with respect to y. That gives you 2y. And then you put together the gradient vector as 2xi plus 2yj. And then in the past, in chapter 14, we plugged in values and we knew that the gradient pointed in the direction of steepest ascent, and we used it to compute directional derivatives and things like that. But you can also look at the gradient as a vector field that just generates a vector at any point on the xy plane. So here we are going to, in this example, in this exercise, we're going to look at what these vector fields look like. And we have 3 different contour plots, and then we have level curves, contour plots, and we have the corresponding gradient vector fields, but they are not in the right order. So we want to match. So over here in the first row, we have 3 level curves. And let's just look at the first one. I'm just going to do the first one, and then you can do the other ones. But what can you tell me about the gradients that belong to the function that is shown in that first contour plot right here? So we see our contour lines, and let's just assume that the values increase going from left to right. Then you remember what it means that contour lines are far apart or that they are close together? They tell you something about the steepness of the surface. And the closer together the contours are, the steeper is the terrain. So if we wanted to draw gradients at different points right here, so for example, up here that I just drew, and compare it to the gradient vector at that point, we know gradient vectors are perpendicular to level curves, so that's good. So we know that they are going to point straight to the right, if that's increasing values. Now, how do these 2 vectors compare? Well, over on the right point, our contours are closer together. So if I draw that vector in right here, then by comparison, over on the left, the vector would have to be, well, what do you think, shorter or longer? It would have to be shorter. Oop, that doesn't look much shorter. Let me draw it a little bit shorter. It would have to be shorter because it's less steep. So the steeper, the longer the gradient. And so if I draw in the gradient over here, it's even longer. And so my gradient vectors get longer the further I move to the right. And then I have lots of symmetry going on. So all the gradient vectors for each level curve have the same length. So once I choose a length, that's the one that I get for that level curve. So it looks somewhat like this. And so which one is it? It's not the first one, it's not the second one, it's the one over here in the lower right. So that behaves in the way that our level curve